This video will walk us through an implementation of an UML profile for IoT PML as a domain-specific modeling language, defining metamodel constructs, rules, and theories applicable and useful for modeling IoT devices, illustrated by examples. The IoT PML domain-specific language is represented by architectural views. Architectural views are representation of a system from the perspective of a related set of concerns, typically relating to a single stakeholder or stakeholder groups, such as optional, colored in gray, and IoT PML, colored in yellow. The optional architectural views provide a great set of supplementary diagrams showing your system from other aspects beyond the core views of IoT PML, which is focused on a software stack. Before we dive into the metamodel, let me say a couple words about each view and their relationship with each other. The context view facilitates a common understanding of how the system under development fits into its intended or existing environment in terms of external systems and human actors factors. The subsystem view hierarchically depicts the decomposition of the system under development into system components which are later realized as either software or hardware solution. As such, it provides an overview on how each individual system component fits together. Software stack is essential as basis for a definition of a software architecture skeleton and subsequent design activities. It captures the IoT hardware, software stack, and non-functional requirements as well as functional properties. And threat model proactively identifies potential security threats in your IoT solution and addresses them prior to its production. Okay, now let's have a look at the modeling constructs of system context diagram. So I will open that. So here we see on the very top an element which is stereotype element. And this element represents any type of element which is used for modeling IoT devices. This element can be type of a device, system, and service. As you might have noticed, the device can be other three kinds. It can be either a control unit or sensor or an actuator. So the device represents a generic device, and if you want to be more concrete, you have the option to pick either sensor, actuator, or control unit. Then there is a flow between device and the system element. The flow, in fact, is a relationship type, which can either convey information item or a signal. Depends on what level of abstraction you are building, or in fact what type of information you want to model. Okay, so that will be information flow. Let's come back to the stereotype system. System, it usually represents a system under development, and this is your system, which later is decomposed in the following steps. Then also the system can interact with a service. Service represents, it can be either a web service or it can be any type of service treated as an external system. So I forgot to mention device, service, and user. Those are treated as external entities. User, it in fact represents a human being. That's why here is the extension of the meta class actor. So now let's have a look at some real example how this meta model can be used in a project. So here you see a context diagram which of a concrete system, which is in this case called vehicle detector, and here we have this device type sensor, which has some information flow which conveys some information video stream from camera to vehicle detector. And on the other side, we have a monitor, which is a device type. And here we have a service. And the service, in our case, is a software application which receives some vehicle detection data provided by the vehicle detector. As you can notice in EA, it's implemented into IoT PML is implemented in a way that it can change the shape of the elements, as you see over here. But about that, there will be another video talking about a concrete implementation of IoT PML into enterprise architect. So let's go back and let's have a look at the system decomposition. You might have noticed that we have more diagrams in this concrete architectural view. This is because it makes the metamodel more readable. So let's have a look at the first diagram, which is called the system decomposition within the system decomposition architectural view. So I will open that. This system decomposition, again, there is the high-level element. As you already know, that's an extension to the metaclass class. And this element can, in this case, for the system decomposition, is it can be type system or system component. Coming back to the splitting all the architectural views into diagrams. So what you see in every diagram, you see only those elements which are needed to create the particular diagram type. So in this case, for the system decomposition, you would use only the system and system component and hardware component, software component. You already know what the system is. The system is the same element what was already introduced previously. So this element is reused. So you don't create the element again, but you reuse already existing element from the system context. So let me interpret this metamodel. So the metamodel says that the system is comprised of one up to more system components. The system component can have some references to external entities, which that can be described by a file. So the file can be some path, either to some URI or a local path. And therefore, there is the abstraction. So the system component can be a type of a hardware or software. The practical use of the system component in reality is that first you decompose the system under development into system components, and then later, when you already know how this system component is going to be implemented, you later transform the system component element to either software type or hardware type. And as you see over here the hardware component can be comprised of 0 up to many other hardware components. So you create very nice system decomposition. In this case, the same applies to the software component, which represents any software parts of the system. And to assign this software component into a particular hardware component type, you just use the relationship abstraction. So by doing it this way, you indicate that, hey, on this hardware, there is this software component running. Again, I will show you an example of a system decomposition diagram. So it looks like a tree hierarchical structure. I will move it a little bit aside. So you have the system, which is this element, then is decomposed or comprised of, here in this situation, you don't see the system components anymore. So you see already a concrete hardware or software component types. So that's how it is. Okay, so let's go back. So there was system decomposition, and now let's have a look at the system interfaces. The system interfaces, it reuses the same elements what you already identified in a previous step in the decomposition of your system, but you just add to the already known system components, you add interfaces. Interfaces at the highest level. So the interface is a classic meta-class interface, which can be either provided or required. So that's the lollipop versus socket. So every interface is exposed by these two elements, and the either provided or required interface is realized or is connected to the interaction point. Interaction point, as you see over here, is just an extension of a port, so the visual appearance is the same like a port. And the relationship between the interaction points is a connector relationship. And as you see over here, the system component embeds one up to many interaction points. So it means that every system component embeds owns one up to many interaction points. And the system component is also, if you want to model a behavior in a way that you model it at this level of abstraction, you model behavior as an operation. So high level operation, like what is this component supposed to do. So we just stereotyped a classic operation by behavior, so it can have 1 or 0 up to many behavior or operations, and that's why there is the ownership. The same thing also applies to the interface. The interface as such, it can also own a behavior. The reason why there is also the relationship between a system component that there is the ownership is that every system component can override the behavior defined by the interface. So in case if you want to create some different operation compared to the interface definition, so you just create a different instance of the behavior just for the sake of the system component. And the interaction point, there are two type of connectivities or two type of relationships between the interaction point and device and service. Again, the device and service both stereotypes were already introduced in a system context, and the relationships can be in information flow or a connector. The reason is that the connector can merge the interaction flow, so it eventually looks like this. As you see, here is the example. So here is a connector, it creates a layer above, and there might be 1 up to many interaction flow. So here is an example. So here you see the vehicle detector visually identified by the boundary, and here you already see those known system components which the whole vehicle detector is composed of. And here you see the example of interaction point, and the interaction point can be connected with the device or service or another interaction point, as it is seen in this situation. Okay, so that was the system interfaces. And now let's have a look at the software stack. As you see over here, the software stack decomposes hardware and software components from the identified in the system decomposition. So first let's start with the layers, because the layers, they play a very important role when it comes to defining the model structure. So what is the layer? the PM layer, platform modeling layer, it identifies the software stack architecture in a way that you can have the PM layer, every PM layer has a layer ID, and the PM layer can be a type hardware platform layer, application layer, hardware abstraction layer, driver layer, or a system layer. So if we talk from the top to the bottom level, so first you start with the application layer, where everything related to application software is within this layer, and then you go slowly down to the system layer if needed, and in fact you use only those PM layer types as you need. The package meta class is extended. Is the PM layer is an extension to the package meta class, and every element which is just highlighted, the PM layer, implementation repository, interface repository, and design repository, have inherit the URI string, so there can be again linkage to some external resource. And what are these three elements? So the implementation, interface repository, and design repository. The implementation repository is owned by the PM layer, and the same thing applies to the interface repository and design repository. It means that the every layer type will have all three packages type. Now let me talk about the purpose of each repository. So first let me start with the interface repository. So the interface repository, it's a repository where you identify the potential interfaces, and you define a behavior, as you already know, the behavior meaning the stereotyped operations of each interface. And that's it. It's like really just an interface library, if you will, stored in the interface repository package. Then there is this implementation repository. So the implementation repository is a repository where you identify either hardware or software components which you link to the already identified interface repositories, and you either realize or you use the interface repository. So you just define the implementation. Also here you can define a behavior, which we will talk about a behavior later. And then the last design repository package. Design repository serves for visualizing concrete instances of the elements, software or hardware components identified in the implementation repository. So the design repository also there can be some linkage to concrete implementation realizations, libraries, and so on and so forth. So that would be when it comes to a structure of the different layers within the software stack. Okay, so that will be the packages. Now let me go first through the interface repository. You already know what the interface repository is. Now you finally see some examples, and you see a concrete meta model of the interface repository. So you already know that the interface is the main element which is owned by the interface repository, as you see over here. So one interface repository is owned or owns one up to many interfaces, which owns 0 up to many behaviors, which is the operation type, which I already talked about. And here is the option. Once it's done, the interface repository also has the option that if you use some external libraries and you just want to reference, hey, this interface will use this this external library just to reference for perhaps code generator, you can do that by using the relationship realize between the interface and the implementation element stereotype, which is meta class, which is an extension of a meta class artifact. As you see over here, the implementation element type can have these subtypes: source code, package, file, library, cards, component, in-house component, and so forth. Okay, here is an example. Interface package. So you just see interface definitions and their behavior. Okay. So interface repository, implementation repository. So in this repository, so let me start from this element. So this is the package, owns 0 up to many system components, and you already know that the system component can be either software or hardware according to what layer of the software stack you are describing using IoT PML. And yeah, the most important thing is you have a system component, either software or hardware, and it can either use the interface, which was already predefined in the first interface repository, or it can be realized. It means that it implements this interface. Here there is this specialty for hardware component. The hardware component also can be a special type, which is a hardware component which represents addressable elements. The addressable element is that part when IP exact comes into play, and if you have IP exact definition elsewhere, this is exactly the metamodel part which takes care of visualizing the IP exact XML file on a diagram using these elements. So here is the special hardware component type addressable element, which has base address and has some width, and also it can have the addressable element can be a type of either register or a field. The register here, there is the volatile, whether it's true or false, and can have some offset. And the register can be composed of some fields which has this access, which the access type is defined by this enumeration: read only, write only, and so forth. And here can be possibly a concrete value. So first let me show you this specialty for the hardware component. This one. So here it is. Here is an example that you have a hardware component which is comprised of registers and fields, and here we have some concrete values, and yeah, and the same thing applies to the hardware component. Here you see the realization. This is the situation. You have realized relationship type with already existing interface, which has a concrete predefined operations or behaviors, if you will, imported from the IP exact definition. So here is one example for the hardware components. Here is an example of lower decomposition of the whole system. In this case, it's a software decomposition of one software component which was identified in the composition. And here actually is the point and the reason why we split the architectural views into the optional and IoT PML. So I think you already got the idea that using the IoT PML, you can just skip context and you can skip the composition, and you can just do the composition instead of system decomposition. You can use this implementation repository, and you can create the decomposition tree, the hierarchical tree, using just the IoT PML. But it's up to you, really. That's why it is optional. So, and here is a last example, typically how you're gonna use it. So you have the interfaces stored and defined in the previous step in the interface repository. Then using the either use or realized relationship type, you just link it to a concrete software / hardware components, depending on what layer you want to visualize, and that's it. So this is for the implementation repository. Okay, and now let's have a look at the design repository. The design repository, I will start from the package again. So this is the package design repository, which owns instances. This is the most important thing. So you use instances of the elements identified in the implementation repository, and these instances, as you see here, those are type of either hardware component or software component, which are exactly those two what we already talked about earlier. And those instances, they can embed required interface or provided interface, and then again the required or provided can have information flow between the interfaces and external entities such as device and service. So here we see again for the clarification that the provided interface and required interface are just elements which exposes the main interface identified in the first step in the interface repository. And here is an example of the application design. So we see clearly the composition, we see the nesting of the concrete components, and we see the required versus provided interfaces using the lollipops and socket visualization. And yeah, we see the flows between the external parts. So this is very important. Still keep the track with the external entities to not to lose track of the reader of your model. And here is something what I'm just going to talk about right now. This is a new element, and let me explain that. Let me explain that later when we talk about something called NFQs. But before we talk about the NFQs, let me open the behavior. Every system component, again, either software or hardware, can own behavior specification, and the behavior specification is nothing less than an activity, a special type of activity called the behavior specification, which owns something called control point. The control point is exactly the point which you stereotype the concrete behavior specification, which you would like to do some measurements. Either you require some functional or some results, so you look at it as a requirement, or you already put there some measured values. More about the requirements and measured values later when we talk about the NFQs. The control point is a special type of action, and the action can be either call operation or call behavior, depending what level of behavior specification you are describing. So let me open an example. Here is an example, just a classic activity diagram. The activity diagram starts with or is wrapped by the behavior specification. So that's the big one. And then we have actions, which in this case it's just calling an operation. The operation is linked to the operation defined in the either system component or it can be an operation defined by an interface. And if we want to do some measurements, then we will stereotype this action as a control point, as you see over here. So you have a stereotype control point and over here. So now let me finally talk about the NFQs. The NFQ stands for non-functional quality, and non-functional quality can be this type, can serve as either description or a requirement. I already mentioned shortly before what it is, but just for the sake of clarification, I will say it one more time. The description serves for back annotating the measured values back into the model. If you use the NFQ kind as a requirement, so then you look at it as a value what is expected. So you're supposed to design such a solution which would meet the requirements of the non-functional quality. So that was the NFQ kind. Then the value, the concrete value of the NFQ kind can be set as a constant value or value triple, following these rules. So the constant value, you just use this syntax to define, or in case of the value triple, you just feel free to use the min max or average notation. Okay, so then the NFQ, we differentiate between three types: duration, memory, and power. The memory and power, those two can be linked to any system component type, depending on a level of abstraction, what you model. Memory, it defines a special type of element which usually use the NFQ type memory on the footprint, how big it's supposed to be and versus how big it is, in fact. And the duration, it has a very strong relationship to the behavior, because this is the special kind on a NFQ, which is only linked to the control points. And as you already know from the NFQ, from the behavior metamodel, so the control point is an action, is a special stereotyped action, and the NFQ duration, that's the only NFQ which has two relationship types. First, identifying the start of the measurement, and then the second, identifying where the measurement stops. So you clearly define the branch, what you want to measure or what requirements you want to apply. Okay, the stop and trace, those are just extended the meta class of the relationship trace. An example of this meta model, so let me show you this example. So this is a nice one. So here you see behavior specification. Again, this is an activity. And here you see different actions. In fact, you see this is just an atomic action, which is also sometimes needed, just an initiation in this case. Here we have this fork symbol. It indicates that this is a call behavior. So we have another behavior specification, and this control and this call behavior invokes the already known activity. In this case, it's a read video input, and as you see over here, the relationship, that's exactly this start trace. It's linked with NFQ duration type. In this case, is recognition, and you see the value is has to be less than 1 second, and the constraint type is a constant value, and it's a requirement type. So it means that I expect that this this behavior starting here up to here to this control point will not go over the one second. Okay. So this is an example, and the last but not least is the threat model. The threat model is clearly something which, although we have it optional, but we highly recommend to model security because it plays a very important role when it comes to IoT PML. And the threat model, metamodel, is very simple. It's reusing these elements identified in the context. You can do the threat model at various levels of abstraction, and you just use the stereotypes used in the DFD, except there is this one element which has a special meaning in the threat modeling, which is the PML threat, and it has some enumerations assigned to the typical DFD diagram stereotypes. Let me show you some example of threat model showing the system. In our case, it's a vehicle detector, showing at the context level. So here it is. We just use trust boundary element, which identifies the boundary of some, if you will, enclosed system within a system, and you define some data flows which are used, or which are visualized using this relationship data flow. And okay, with that would be it. And this is how the whole meta model of IoT PML looks like. In other video, you will see how this can be implemented in Enterprise Architect, and you will see some real cases.